This question prompts us to use de Moivre's theorem. This can be found on page 20 of the formula book, and it states that r times the cosine of theta plus I sine of theta, all raised to the power of n, is equal to r to the n times cosine of n theta plus I times sine of n theta. Before we delve into this further, let's quickly recap the idea of polar form. If z is a complex number with magnitude r and angle theta, then we can write z is equal to r times cosine of theta plus I sine of theta. It's worth pointing out that this is the exact same expression that appears inside the brackets on the left-hand side of de Moivre's theorem. This means that we can only apply de Moivre's theorem to a complex number which is written in polar form. This poses a bit of an issue because it's not how z is presented to us in the question. Thankfully, we can use our calculator to convert z into polar form. We're told that z is equal to minus 3 plus I. One way to write this would be minus 3 plus 1i. This means that z has a real component of minus root 3 and an imaginary component of 1. So, how can we convert this to polar form? Well, I'll guide you through how to do it on the Casio calculator. We'll need to type in the following: pole of minus root 3, comma 1. The pole appears above the plus in yellow. To type this into our calculator, you would need to press Shift followed by the plus sign. The comma appears above the close bracket in yellow. So to type this in, you would press Shift followed by the close bracket. When we type this into our calculator, it will return the following output: r is equal to 2 and theta is equal to 150. These refer to the magnitude and the angle of our complex number. Using our definition of polar form above, this tells us that we can write z as follows: z is equal to 2 times the cosine of 150 plus I times the sine of 150. The overall goal here was to find z to the power of 4. De Moivre's theorem allows us to find the power of a complex number, but it must be written in polar form. Well, we found how to write z in polar form, so let's write this in. Now, we can apply the statement of our theorem with r equal to 2, theta equal to 150, and n equal to 4. Now, let's simplify. 2 to the power of 4 is 16, and 4 times 150 is 600. We can evaluate the cosine and sine on our calculator. Cosine of 600 is minus a half, and sine of 600 is minus root 3 over 2. Finally, we can multiply in the 16 outside the brackets. 16 times minus 1 over 2 is minus 8. 16 times minus root 3 over 2 is minus 8 root 3. So our final answer is that z to the 4 is equal to minus 8 minus 8 root 3 times I. We are asked to find t in its simplest form, where t is equal to z times w. This means that t can be found by multiplying together two complex numbers, z and w. The key to solving this question is the following. To multiply complex numbers in polar form, multiply the magnitudes and add the angles. In part A, we found that z has a magnitude of 2 and an angle of 150 degrees. In this question, we're told that w has a magnitude of 3 and an angle of 30. To find the magnitude of z times w, we multiply together their two magnitudes. This gives us 2 times 3, which is 6. To find the angle for z times w, we add together the two individual angles. Here, we'll get 150 plus 30, which is 180. This means that t, which is equal to z times w, will have a magnitude of 6 and an angle of 180 degrees. Remember, if we know the magnitude and angle of a complex number, then we can write it in polar form. T has a magnitude of 6 and an angle of 180, so this means we can write t as 6 times the cosine of 180 plus I times the sine of 180. Using our calculator, cosine of 180 gives us minus 1. Sine of 180 gives us 0. I times 0 is 0, so this simplifies to 6 times minus 1, which is minus 6. So our final answer is that t is equal to minus 6.